Please join me right now in welcoming Mr. Scott Willoughby.
Thank you very much, Jeff. I'm going to work from my lapel mic so I can wander around here. I'm from New Jersey, so I'll speak with my mouth and with my hands. We'll see how that portrays. I want to thank Jeff. I want to thank SME and all of the sponsors for the AeroDef conference here in Long Beach. I'm a 27-year veteran of the space industry, and I certainly have the job of a lifetime being the program manager for the James Webb Space Telescope, which is the scientific successor to the Hubble Space Telescope. So I got a really cool and exciting set of charts to go through. This is something I came up with about a year and a half ago, that what I call basically JWST by the numbers. I get a chance to explain to you through each of those numbers what makes it impressive. I'll try and translate it to engineering. What does it mean to build a telescope? A little bit about science. You can ask me science questions at the end, but I normally travel with a scientist to answer those, so I'll be a little shallower in that area. But I got a little bit of grip after the last 6 years figuring out what the telescope's going to do. But my job, Northrop's job, and working for NASA at Goddard is to build this telescope and get it on orbit. But I want to start in concert with your coffee and my loud voice. I want to kick this off with a video that I think will give you a good charge as to what the telescope is all about, and then go into it.
The eyes of the world now look into space. We mean to be a part of it. We mean to lead it.
We are a spacefaring nation. Pioneering is what we do. Today, we chart a new course that takes us beyond our wildest dreams. An exploration that requires a new craft. Currently under construction is a marvel of engineering that will reveal the dawn of time. And behold, the epic of creation. Where did we come from? Are we alone in the universe? The answers are on the horizon. The James Webb Space Telescope. America's next bold adventure.
Now, I don't know about you, but I get goose pimples when I hear that video. I've given this talk to a lot of folks. I've gone from elementary school students, college students, Congress, and go through. I don't always show the video. I showed that video to the set of high school students about 6 months ago, and I actually quizzed them whose voice was at the beginning of that. Now, I'm guessing everybody in here knows who inspired us into the space race and landing men on the moon. Well, 30-some-odd high school students couldn't name JFK's voice. I asked everybody to guess. One person said Eisenhower. All right, you're getting in there close. It shows you, right? We've had an evolution. We've had things that inspired us to become engineers or be a part of this industry. I mean, I'm space. Other people have done it through, the airframe world and what's going on through that stuff. But this program is a chance for us to reinvigorate that kind of thrill as to what it is. Hubble has done that. The James Webb Space Telescope will absolutely bring people's curiosities to a peak. So let me tell you a little bit about it. And I told you, this is called JWST by the numbers. So the way this presentation will go for all you engineers in there, I'm going to throw up a number, then I'm going to tell you a little bit about what that number means. So the first number is the biggest number I could think of. It's 13,500,000,000. And for those of you who are curious about the universe and its start, you could probably guess that's pretty close to how old the universe is. So as scientists go today, they would say that our universe is 13.7 billion years old. Now, amazingly enough, scientists could say plus or minus 100 million as if it doesn't matter anything. If I'm off by a day on my schedule, I'm going to get my butt kicked. But these guys got plus or minus 100 million years within their latitude. What the James Webb Space Telescope is going to do as one of its primary missions is actually look back that far in time. We will look by looking further back in distance That's basically how you see back in time. When you walk out today in beautiful sunny California, I'm from New Jersey originally, I love living out here. You look at the sun, and that light took 8 minutes to get to your eyes. You never see things as they are other than, being this close. Speed of light's relatively instantaneous. But the further you see these distant objects, the more you're seeing their state as they were. It takes that long. We're going to collect the faintest of light. We're going to go back to the time that the very first stars formed. People ask, well, why didn't you go back 13.7 billion years? Good question, I stole it from you. The answer is, well, the first couple 100 million years were basically dark. So our telescope is looking for photons. So until helium and hydrogen, after that Big Bang occurred, came together, started the fusion process, and created stars, there weren't any photons for us to collect. So we're basically going back as far as the first light. So we've been called the time machine, the first light machine. That is an amazing part of this mission. The other part of this mission, which doesn't show in this chart, I'll probably talk to it maybe a little bit more on there though, is we also have spectroscopy on here, near infrared and mid infrared. We have the ability to see the light as it goes through the atmospheres of now 1,000+ exoplanets, planets around other stars. And by using those instruments, we'll be able to tell if those atmospheres support life. We will take us that much closer to understanding, are we really alone in this universe, and where that life could be. At least life as we know it, carbon-based, exhaling carbon dioxide, breathing in oxygen, photosynthesis, and the reverse of that process. So we have instruments that are that sensitive. So it's an amazing mission. So the next big number I can come up with was 1,500,000. Sure, it's a lot smaller than 13 billion, but still a big one. Well, that signifies how far this telescope is going to go away from Earth in kilometers. Now I'm going to switch back to miles. That's 1,000,000 miles, but 1.5 million was a bigger number, so I started in kilometers for you. So we're going to go 1,000,000 miles, 1.5 kilometers away from Earth to Lagrange point number 2. This mission is in the infrared. We have to get cold. I'll talk about that later, cheating on some of the other numbers in there. And in order to do that, we can't be like Hubble. We can't be 250 miles-ish, above the Earth's surface, because this is just a big glowing, planet. And obviously, it's that much more difficult than to block the sun and everything. So we're going 1 million miles away from Earth. We're going to Lagrange point 2. And as the Earth goes around the sun, we will actually follow the Earth in its path. We'll have our own 365-day orbit. So we're orbiting the sun. We get to keep the Earth and the moon behind us. That enables this mission, again, to look for this red-shifted light in the infrared, which is the only place we're going to find this old information. So we have to get out there further away, making it a very challenging mission. The next two numbers, quite smaller numbers, but I pair two together. This starts talking about the engineering prowess of what we're doing with a telescope like this. 40 and 178. This observatory on the right is 75 feet long, by 40 feet wide, by 40 feet high. Those of you in the space industry know your standard fairing is going to come as 5 meters. Let's call that 16 feet you have to fit in a diameter. Well, we have to deploy to that state, which means we have to stow ourselves. We're an origami, a transformer telescope. We have to start off with our optics stowed, with our sun shield stowed, with everything tied up into that package, and then release. In order to survive that rocket launch, we have 178 release devices. We call them retention devices, but we name them after what they need to do, which is then release on orbit, and 40 deployable structures on this. All of these have to work, and I'm going to show you a deployment video on 2 weeks from launch. As we're on that path, we have 2 weeks of deployments. Curiosity had 7 minutes of terror. We have 14 days of holding our breath to get this thing deployed as we're traveling, to 1,000,000 miles away from Earth. So obviously you can see the engineering challenges of building a telescope this big. Minus 388. Let's go negative with our numbers. Figure there's a fun one there. I already cheated. I said we're going to be cold. And you guys, if it was later in the afternoon, you would have yelled, how cold is it, right? But I know the coffee hasn't kicked in yet. Well, there's the number, and that's in degrees Fahrenheit. I could say 38 Kelvin, but again, I wanted a negative number at this point in time. So the cold side of this telescope, in order to get optics cold enough to see the faintest photons in the infrared, near and mid-infrared wavelengths, has to operate at near minus 400. The hot side, which is always in the sun, also our solar array there, converting our electrical power, is going to be close to 200. So we create a 600-degree differential, and we hold those optics stable to better than 20 nanometers on a 6.5 meter scale, 7 times the collecting area of Hubble. So collecting light is all about having a wider set of optics. I use an analogy in our drought-stricken California here. You know, if it's going to rain a ½ an inch, doesn't sound like much. And if you got some bucket out there, it doesn't pay to have a taller bucket. So, but at least if you have a pool, you know, you got a bigger diameter. We're collecting basically photons like you would collect raindrops. The wider you are, the more chance you have of collecting those very faint photons. So we're going to be operating one side at -400, I'm just rounding numbers, the other side at -200. That thermal design, one of the things we show in the picture here is just a little teeny person standing inside of a sunshield membrane, 1/1000th of an inch thick Kapton. We have 5 of those membranes. One of them is 2/1000ths of the inch. The other are, 1 mil each. Between that and other thermal properties to isolate the hot side from the cold side, we can create a 600-degree differential, which is obviously quite impressive. And then I threw, one more number before I kind of go into the pictures and tell you what's going on. I said 10 plus on here because that's how long we're going to operate this telescope on orbit. Its mission life, and the cool thing that you can see there is right now Hubble is predicted to go to 2020, 2021 after its last servicing mission in updating some of the componentry in there. It's been updated to last about that time. And as you know, it's all about flying it and orbital dynamics. For us, basically our life-limiting property is expected to be the fuel tank. So we will be 10 plus depending on that, the observation profile and offloading momentum as we're accruing in our reaction wheels. So we're a 10-year mission life to go up there and launching in October 2018. So what's going to show behind me now, and I'll kind of talk through it, is that deployment sequence. This is a video that you can go on YouTube and go home and show your family and say, hey, look at the James Webb Space Telescope. I got a chance to talk to the guy who does this and how this thing gets up there. I mentioned it's going 1,000,000 miles away from Earth. This video picks up from after separation from the top stage. At the top, it says mission elapsed time. You'll watch that fit and start, right? We're not going to spend here. It takes 29 days to get there. We've sped this up into 3 or 4 minutes. So you see true mission time. At the bottom, you'll see a highlight of both the distance where we're at and what the operation is. And then on the bottom left here, you'll watch our path as we go past the moon. Moon, for reference, 250,000 miles away from Earth. We're going 4 times the distance from the moon. So when you first get out there, obviously the first thing, I already missed it, but what you kick off is a solar array, right? You got to get your electric power. We can do a number of course corrections as we got to tilt and cant this. One of the most amazing things for us is we actually have to initially go up there in a rotisserie roll. Since we define composites to work at -400, we really don't want them to see much of the sunlight before a sun shield deploys and go through T sub G on the glues. So we got to keep those hot points balanced, so we rotisserie roll. We get up there, we move out our solar array, we move out our high gain antenna so we can start that communication, get off the omnis, start talking, to Earth. And we get in there, and at about this time, we just passed the moon. We're on day 3. We actually passed the furthest that man has ever been from Earth, which is Apollo 13, when they had to use that gravity assist to come around the backside. And then we start open one of the most amazing parts of the product here, which is the sun shield. The sun shield, again, 75 feet long, 5 feet wide, 5 layers of super thin Kapton. Between that, the tensioning, and basically the venting design, when this thing deploys, it will again create that 600-degree differential. It deploys like a clamshell. We get the first side out coming from the front, the aft composite structure. It's basically a composite structure, everything's bonded onto. We open up the back. When we do, then we can separate the telescope from the bus, creating 1 layer of thermal separation and the space for the sun shield to deploy. After we pull the optics up, you can see the blow up in the top left. We unfurl some covers, protective covers for contamination as we go up there. So they go in actually in that case, the aft and then the forward. And then the core in the center, and then eventually you'll see what we call our mid-boom release. For For those like me who have an old car with a telescoping antenna that still comes up, not built in the windshield, you're familiar with that. So these are basically nested telescoping tubes that get driven by a stem tape deployer. We push one side out, we get the width there. We push the other side. In that case, you can see the nested telescoping, right? The various sizes of the tubes there that pull those membranes out. And then effectively we have motors and pulleys and catenary lines, fishing line, and effectively, through there. And then we start tensioning the membranes. So we initiate the motors to turn on, and then those 5 layers need to separate, and the distance between those layers was calculated pretty precisely in order to enable basically the way that we create this thermal differential. Is part of it is just reflecting the sunlight back in the heat. Everything that gets through the first layer, a chunk of that then radiates out to space through the venting. Then the next part gets partly reflected, it goes through. Basically took us 5 layers in order to complete the feat that we needed. Now we have a sun shield deploy at day 7. We're still holding our breath. And then we start getting ready. We kick on a cryocooler. The telescope's passively cooled to 38 Kelvin. One instrument goes to 6 Kelvin, the mid-infrared, with the aid of a cooler. The tripod then comes out, and we deploy the secondary mirror. The way that the optics are, they collect the light on the primary, fire it off to the secondary, and then back right down the center into the center hexagon where the optic bench feeds the instruments. Our deployed optics start deploying, one wing at a time. We're on day 13. The next wing will deploy from the other side. You'll see it coming around. We have now 18 beryllium mirror segments, all there. Day 14, we finish deploy. It takes 15 more days to get the rest of that 1,000,000 miles. Day 29, we're out at L2, and then we start zipping around in this Lissajous pattern. Basically, it's somewhat of a semi-stable point there. You got to create an orbit inside of an orbit, and then we're out there 1,000,000 miles away from Earth, and we start breathing again. So that's a cool video to see basically the awe of what it takes to build a telescope with 7 times the collecting area of Hubble that has to get on there. And I thank the team that pulled that together. So let me add in a little fun facts and talk to this side of the room. One thing about coming over here. So the James Webb Space Telescope, interesting enough, for those who follow science, you're going to realize that basically everything has been named for a scientist. Herschel, Planck, Kepler, Hubble itself, right? All of these famous folks. We're named after James Webb, who was basically the second administrator in the 60s. He was there during Gemini and Mercury and Apollo. Retired in '68 before the actual landing on the moon. And the reason they named the Space Telescope after him is because he had the vision for NASA to do more than just landing man on the moon. His vision was, if we're going up into space, let's do something noble when we're there. So they really credit him with, the Compton Gamma Ray, the Hubble Space Telescope, basically influencing NASA to invest money into science. So with that, he gets a telescope named after him, and rightfully so. I mentioned that we're a 6.5-meter telescope launched in L2, successor to Hubble. And we mentioned Spitzer there because it's also an infrared telescope, not as sensitive. We have 4 instruments all operating in the infrared, near and mid-infrared. And we're partnered, it shows there, with other countries, the European Space Agency and the Canadian Space Agency. European Space Agency actually built basically 2 of the instruments, the near-infrared spectrograph and the mid-infrared instrument, part of it. It also got built up by JPL to finish it out. Canadian Space Agency built our fine guidance and a near-infrared slitless spectrograph. So they've contributed to this program. And we're going to launch, I don't know if it says it on here, probably not, but as a part of ESA, we're launching on an Ariane 5 rocket. This is launching out of French Guiana, and that's also a part of the contribution of ESA. So in doing so, they contribute to the telescope with their instruments and their rocket, and they get some priority time for their scientists as they issue out the time when we're on orbit. We work with Goddard primarily. However, Marshall, JPL, and Johnson have huge roles in this in terms of testing and assembly. Obviously proud as Northrop Grumman to be a part of this. And then the Space Telescope Science Institute, they're operating Hubble now on the Johns Hopkins campus, up there in Baltimore. They're going to operate Webb. So basically hand the keys over, and they get to operate 2 of these and together, which is kind of cool. And it's always cool to go to a meeting and see a Nobel Prize winner, John Mather, who got his Nobel Prize for effectively the cosmic microwave background from the COBE observer. So So now I got a few pictures in the fun to show you the progress. You know, said we're going to talk about the design, but the development of this. We're real. We're going to launch in October 2018. I probably hadn't said that yet. We're 2.5 years away from launch. As what you can imagine how complex our verification cycle is. That means we have parts now. I'm going to show you real pictures. But this breaks down the telescope into 4 pieces really quickly. You've got a telescope element, simply stated, that is the light collector, the big optics, again, 7 times the collecting area. That telescope collects that light and ships it back to a set of 4 instruments on the back side of that. That telescope and the instruments keep cold by the sun shield. And everything obviously sits on top of a spacecraft bus, as every spacecraft does, to give it its command and control, power, you know, and all the other things you need, data handling and shipping back to Earth. This is a picture of the 18th mirror on February 2nd of this year being installed on the telescope. That robotic arm, controlled precisely, has just finished the installation of 18 mirrors. And what you look at right now is a fully assembled set of primary optics for Webb. There's covers on it right now. Obviously, we want to protect the surface of those mirrors. Those mirrors, each and every one of them, are made out of beryllium. They work very well at cryogenic temperatures. They're very stable thermally at the temperatures we're going. They were polished to a spec of better than 20 nanometers surface figure error. At that point in time, you're basically near the atomic level. You're kind of polishing, you know, small dots off of the level. Somebody gave me this reference that if we had to basically flatten the continental United States from LA to New Jersey and spread that out, you would have to take the mountains out, you know, kind of fill in, you know, the valleys in there. You'd have a bump, about average bump as high as 11 inches, you know, over 2,500 miles. So we polished mirrors that took 8 years to build with 9 machines, 18 mirrors, you know, at some point in time, 9 of them going in parallel. Those mirrors in a couple months will have those covers taken off as we have to turn this to the side to put in the instruments. That's going to be one of the greatest pictures, you know, ever. So obviously, just the celebration for us getting the 18 mirrors is big. Now we need to take the covers off and show the world with a, you know, big set of shiny gold. People ask sometimes why it's gold. I hate to steal all your questions. I've been accused of making it as a shiny telescope because it looks cool. It just so happens gold really reflects infrared well, you know, like 98%. And it goes down in angstroms. There's like a couple golf balls worth of gold in this telescope there. This is what the structure underlying those mirrors look like. I should give credit. The mirrors, that subcontract for us was led by Aerospace out of Boulder, Colorado. Did a fantastic job with what, I mean, more than a half a dozen of other industry partners for them. Orbital ATK, at the time, everybody's names changed since we started. We were TRW, they were just ATK. I'll talk about Kodak, who's now Harris, as it went through ITT and Excelis, right? All changed their names in this process except for Ball. But that's the composite backplane, 21.5 feet across, 40 nanometers of precision on a set of composite structures operating cryogenically. And then off to the right, you see that tripod before we mated it up at the hinge line. And then that's as we mated it and stowed it. 2 wings folded back, tripod folded over. That's what the bare composite without mirrors would look like, you know, and that's how it goes in the structure. And I promise you, big smiles on everyone behind those masks over there. That's our spacecraft bus as we were delivering it into test. The spacecraft bus is about 10 feet in diameter. The bottom part there, that last silver part, that's the clamp band. That's the part that sits on top of the rocket and gets assembled there. So basically the loads go all the way up through that composite structure, one of the biggest buses we've ever built, certainly from a load handling capacity and the nadir deck in order to put the telescope on it. And then we did a dry fit mate. One of the most important things in our industry is everything we do is hard. Every computer model we try and get perfect, we don't, or we get close. So what this test program is driven by is build, test, build, test, build, test, build, test. Not build a whole lot of steps, pray that it works, and then if not, go back 2 or 3 steps in that process. So when we got the bare structures together, you didn't have to wait for mirrors. You didn't need electronic boxes. You wanted to make sure those 4 corner feet are going to fit. It's as simple as that. That wasn't in our original plan. We added that in as a risk mitigation, but it's very smart, well spent money in order to ensure that we had that interface there. This is a part of the composite structure that holds those sunshield membranes. I mentioned, a forward and an aft. You saw that clamshell open. Look at how hogged out that is. Only the black part there, the gray part, is what flies away. The rest is the tooling underneath. Weight, mass is your enemy, right? Getting to orbit. As you all know, so additive manufacturing are all the things we do to be very precise about just the right amount of material to survive whatever it is, the thermal or dynamic environment. So we had that's a composite sandwich, front face sheet with a honeycomb core, but hogged out literally to the bare minimum in order to mass. The Ariane rocket can launch about 6,500 kilograms to L2, about 10,000 kilograms. Normally they do tandem ComSats up to GEO, but only 6,500 L2. And we're under that now. We're about 6,400, 6,300 with some contingency. That's good, but it's close, right? It's a big rocket, but there's only so much you can do. And then that's a blow up of that picture. I just think that's a cool one, somebody standing in the middle of our sun shield there. That sun shield is not one piece. It may be hard to see from the angle, but if you'll see a lot of rectangled blocks in there. You can't build one piece of three-dimensional thing 75 feet long. It's like stitching a shirt. It's got 54 gores, different shapes cut out, with 10,000 inches of electronic welds, basically seams, in order to stitch this together. Over that span of 75 by 45, it had a spec to maintain its three-dimensional shape to 0.75 inches RMS. It's coming off the mold at 0.3. We've already delivered 2 flight of these and a 5 set of template membranes. Trailblazed them all once, and now we're building flight, and we're on to the 3rd. And that's me and my wife standing in a full-scale deployed model. I talked about test. Well, we don't just test on the flight articles, we test on test articles. As you could imagine deploying something like this in space, you want to practice and practice and practice. You want to practice assembling it, stowing it, unfolding it, putting it back together. So we created a full-scale mock-up. I talked about 5 template membranes. There they are. And we built them up. We used a metallic structure. We didn't need composites for INT to play around with this. And then we did a full-scale deployment of what that would look like. So that just gives you the size, right, where the telescope would sit in the middle where that hole is and the bus would sit underneath of that massive umbrella. This is a little bit of our path. I talked about, again, instruments and optics. They come together, and in 2016, we are literally within a couple months of putting those 2 items together. And then in early 2017, they end up going to Johnson, testing in Chamber A, same place that the Apollo capsule was tested, modified from a nitrogen shroud to a helium shroud to test at cryogenic temperatures. So it's kind of going to go through, kind of cool story. It was a historic monument transferred over to the Parks Department, right? It tested Apollo, right? This is our history. And then it's like, well, Webb wants to use it. We're going to make it greater, right? We're going to put Webb in there. So they had to basically, transfer it back so it could be modified, right, improved, and now it's in use. So getting a reuse of that massive capital asset. That's happening then from Goddard and then to Houston and then back here to Redondo Beach. In parallel, our sun shield and our bus, they'll come together here in our facilities in Redondo Beach. We build it all together and test it here in Redondo Beach. And we put this one on a barge. Not a C5 transport. It's actually a little too big even for that. We're going to barge it through the Panama Canal and come beachside, come up just like a rocket would from Germany into one of the Ariane boosters, and then come into the launch facility there. So I finished this presentation with one more number. It's the most personal one to me. It's also a nice big number, 100 million. It's a very round number, and it's a very understated number. That's just a picture of my team during one of our big design reviews. Our country will have invested well over 100 million hours of people's lives. People like you, people from cutting machinery or doing the accounting to whatever it takes to assemble and test and get this to the launch base. So this is an incredible commitment of people's lives. As you all know, you work on things and you follow that along with your pride. So this is very important for us to get right. We're doing incredibly well. I was proud to show you baby pictures, so to speak, of our hardware as it's growing up with us now, actually. So we're basically into high school. We're going into college really quickly here. And that's what it takes to do that. And then, this is a good chart to pause on. People will look at this picture and say, it looks like somebody did a watercolor painting of the telescope. Well, we don't look like this on orbit. It's really cool, but this is actually a real photograph, folks. This program is so important that the public knows what's going on that we took a full-scale model, the South by Southwest in Austin, Texas, put it out there at the gaming convention, put a full-scale model on the hill, lit it up with all kinds of fancy lights, and invited people in to understand what the telescope is about. And you know what? One person would come in, start talking, and two or three. One time, John Mather and I were basically almost like a soapbox stand with 2 microphones. Next thing you know, there's 300 people on the lawn. Instead of watching Halo 3 or whatever was going on in the other thing, sitting and talking to us about a space telescope. That's pretty cool. It's cool to see the enthusiasm, right, of the public that these are the kinds of things that we're doing. So we get the chance to do things like that. So we've had this full-scale model in, I think, 14 locations around the globe, this being one of the most impressive ones and certainly the coolest photo that you could imagine. We also invited folks there. This is a cool little fact. We invited the Guinness Book of World Records. We fenced off an area, and we did the world's largest science lesson, astronomy lesson, which had to be 1 hour long by a trained professor outdoors under the night sky. Whatever it was were their rules. And we got people in there, and we broke the record for the largest astronomy lesson there. So that was kind of cool to kind of engage people in the science. So that's my talk. I hope everyone gets to walk away from here, go online. You could watch what's going on in the Goddard High Bay with a camera. You can Google or YouTube up, some of our videos and see what's going on. You could share it with your family and friends. That's all I ask of you is to, pass the word on. And I appreciate your patience and staying awake and have time for questions and answers here. Thank you.
Pretty darn fascinating, wasn't it? Scott, I've got a few questions, and the SME team is going to go around and collect some of the cards with some more questions. So October 2018, should we put this particular date on our calendar for this launch, and what will we be able to see real time?
Yeah, so you definitely should put it down, put it on ink. One of the things I like to be proud of in our schedule is, and this is another thing, right? We know this is going to be hard. As a matter of fact, NASA this morning in their President's Budget 17 request talked about how Webb got fully funded again in the request for 2017 budget and said, also, we know there's going to be issues, but this budget covers both the technical challenges in terms of the cost of people, and we have distributed schedule. We have 7.5 months of schedule margin to launch with 2.5 years to go. We follow NASA standards. We actually increased the standards on this. So ink it in for October 2018. The launch will certainly be broadcast in real time. It is kind of a little bit disappointing in what we have. We have a complicated telescope. I talked about -6, 400 on one side. So people always ask, well, we have cameras for the deployment. Well, you can't really put cameras on the dark side, and they all become conductors of thermal and dynamics. I mean, we're down to, femtowatts and, micro whatever, gradations of dynamics. So it was actually too complicated us to put cameras on the other side. So there'll be pictures and stuff of certainly what we're doing in terms of, the launch and the animation, and then obviously the first pictures from the instruments. But NASA will be broadcasting the launch as they always do. I'm sure they'll watch people sweating in the control center.
Okay, we've got some more questions coming up, but here's a couple interesting ones. Your opinion.
Uh-oh.
Do you believe there is life on other planets?
I absolutely do. I find it almost implausible that we're alone. And when you think about what's going on in terms of life, you also got to think more broadly. There's a great book. It was 5 Billion Years of Solitude, whatever, Lee Billings. And if you look at that, and it goes all the way back to the scientists who sat in a room, came up with the Drake equation, which went through a probability. Is there a planet? Does that planet have an atmosphere? Does the atmosphere generate life? Is that life intelligent? Right, all the way up through all those things. The question of how intelligent that life is, does it look like us? It'll be interesting to see. I always talked about after Webb, we'll build a bigger telescope that'll actually not just look at atmospheres of planets, we'll directly image the surface of a planet. We'll put an occulter in front of the sun. We'll look at land masses. And as long as we find a Yankee Stadium on another planet, we have intelligent life.
It sounded good until I heard that last part. Okay, once the telescope is deployed, what will be the first research priorities?
Yeah.
What do we expect to find?
That's actually undecided, but I was just back in the AIS conference, which was hosted in Florida this year. The Space Telescope Science Institute are basically the arbiters with a bunch of very smart scientists that sit on a panel. Proposals are being started to be submitted now. So it's a competitive process to decide where the telescope's going to point. The missions are about the formation of stars, formation of planets. I didn't mention the other thing that infrared does for you is you look at a Hubble like the pillars of creation, and you look at a lot of call it photography because they're really cameras on Hubble, you'll see a lot of opaqueness though. Things form in dust clouds. That's where stellar nurseries are. Infrared peers through that in its wavelengths and sees planets form right at their native. So it will be pointed either at clusters to see planets that are forming, certainly where we believe we can collect life for the first stars, and then at known exoplanet atmospheres to look at that. I don't know who will win out, but I wouldn't want to be sitting making that decision.
All right. We have lots of questions, so let's fire up here. Does the JWST plan for any robotics service module to either address unplanned deployment events or simply provide refueling to prolong the mission?
Yeah, so we certainly hope robotics at that state, NASA's and DARPA, right, are out demonstrating ability to refuel. We prepared with targets around the launch ring to make it easy for a robotic mission to grab the telescope. So we've made it enabled such that the telescope can be captured, but there isn't an explicit plan right now that says go in, cut off the cap, and refuel it. We weren't designed serviceable like Hubble with line replaceable units where you can slide a box out and in. So you could not replace a box the way the panels are up. But you could deal with fueling or deployments if you can grab onto it and deal with a robotic arm. Missions aren't planned, but we didn't preclude the capability.
How do mirrors stay aligned after the rigors of launch?
Oh, that's good because I forgot to mention that because that's part of the robustness. Part of this, going a million miles away and getting done right the first time. So the mirrors, first of all, they were polished to be precise, and they were tested at cryogenic temperatures at the Marshall Space Flight Center. However, on the back of every one of those mirrors are 7 actuators, one on each corner of the hex and actually a center of curvature. So we can push and pull on that and do that, again, center of curvature. So there's 7 motors, so they are commandable. So we could take those 18 mirror segments and recommand from the ground and crisp up that image.
Okay.
Oh my God, they're still coming, huh?
There's lots of questions here, okay?
I'm gonna grab this water.
What is your opinion of the microwave engine?
The microwave engine?
Yes. Let's see, Joan Ellis asked that question. Where's Joan?
Oh.
John? Excuse me.
No, so my opinion is I'm curious. I mean, from an engine, we're using typical, monopropellant or bipropellant rocket engines. We're not using ion thrusters or anything for our mission. But in terms of other, engines or missions to do stuff, I'm not familiar. We always need more efficient ways for thrust. Like I said, our fuel will be our life-limiting, feature, most likely. All right, I'll look it up.
Okay. This is a 2-part question, Scott. Assuming JWST at 1 million miles out is not serviceable, what sorts of design and manufacturing decisions differ from the previous generation of telescopes like Hubble?
Yeah, so the first thing we mentioned is for our optics. Hubble was a single 2.4 meter ULE glass, non-deformable, non-controllable optic, within there. I mean, you could do things with instruments, deal with and post-processing of data. So we've mechanized the mirrors, so we have full, control over that. Everything that can be redundant is redundant on the satellite, typical for space. However, mechanisms are not, you can't put a second hinge, then just both hinges have to work, right? So you're stuck in that battle. So the robustness of the testing, our factors of safety for ground tests are greater than any standard that you could imagine, right? Everything is going to be, 5 to 3 or 6 dB, greater than its environment. It's going to be subjected to temperature ranges and, at the cryogenic in a box and deployed on a ground test. So basically, it's the increased margins for factors of safety for that, and then any case that we could add in either redundancy or motor control so that we can adjust things on orbit is the bigger things.
The second part of that question is, with respect to design and manufacturing, what are some of the key lessons learned from some of the prior programs that were considered for this?
Yeah, so the biggest lessons learned as we build this up. So So we think of the two major features of this are the optics and then the sun shield, right? So big collecting optics, 7 times Hubble, one large, sun shield membrane. So the biggest things that we've learned throughout this are our ability to test things in a 1G environment in order to offload and simulate that on the ground such that you aren't fooling yourself on Earth that, if that thing just fell out because, gravity helped it, you're not going to have that assist. So our legacy of 50 years in space, and certainly NASA's in there, most of what we developed are state-of-the-art techniques for offloading or doing it. I'll give you a really simple one, and it isn't something we invented, but even the shape of a membrane that size when you put in tension, right? It's sag and do the gravity. A very simple tactic for that one is you take it, you shape it, you measure it in one configuration. You just literally flip it 180 degrees, right? And then you subtract in your models the difference between those vectors out and come up with a 0G shape. Things of that nature and other stuff. So our techniques are built on, other programs and deployables, and we always scan. And it's bigger than just, Northrop, Lockheed, Boeing, all the big space folks and NASA. We share lessons learned. I go to test conferences. This is something that isn't as much a proprietary sauce as we're all better if space is successful.
So how do you test materials and components at negative 238 degrees C?
Yeah, so when we have cryogenic, I mentioned at the chamber A at Johnson that typically for most spacecraft you use liquid nitrogen, and that gets the cold wall cold enough to simulate the space environment for a GEO or a LEO or a MEO bird. You actually have to test with helium, so you have to put a helium shroud in, and with that you can get a chamber down to 10 Kelvin, single digits.
Okay, when creating the mold for the frame, what kind of tool materials were chosen, and was the frame made manually for the most part or with some automated equipment?
All right, good tooling question. For us, our composite structures have such a high degree of precision that are required, where some of our coarser things, we actually use aluminum tools and we can build the composite on that, but the CT mismatch to that would be too great for us. So we actually built a composite tool to do a composite layup such that when we do the curing in the oven, we wouldn't have any CTE mismatches in there. So many of our precision composites are made on composite tools.
Just mix up the questions a little bit here. Scott, your view of the presidential candidates, which are the most space friendly?
So last week I had my media training and they asked me this question, and I think I said no comment. For us, space to a great degree tends to be, to some degree, agnostic. It's personality more than party based. Every president has supported NASA in a different way. What happens in these cycles that's more important to us is how that vision may shift, right, over 4-year times, and if that direction will shift towards, a different mission when we have long-term programs. Webb as a program, we started in 2002, we're in 2016, we launched in 2018. Nothing's changing our track, so Webb is going to be through completion. We're curious as anyone to see if the vision for NASA maybe get influenced by the next president.
All right, you'll be able to answer this one
All
more
right.
directly. What are the top or the most useful skills an engineer or technician would need to work on the telescope or other spacecraft like it?
Well, so the hardest thing I have as a program manager is getting engineers to know how to manage cost and schedule. But we do pretty damn good at that. Our skills are dominated in this particular program by materials engineers, as you can imagine, with materials that are behaving at temperatures. Sometimes we're requalifying existing materials. Some cases it was developing or qualifying. So materials engineers for us were huge in terms of development. And then structural, mechanical design and stress are thing. Everything at Northrop Grumman has started with an M. And mechanical GSE, mechanical stress, mechanical design. I hired them all for our big hump of engineering in there. That dominates it more than certainly our comm programs, which are electrical things and chips and low noise amplifiers, right? In this case, very high mechanical engineering.
Now, there's a word here, I don't know how to pronounce it. Excuse my ignorance.
Beryllium.
Here. Beryllium. I couldn't read that portion.
Yeah.
Why beryllium and not ULE glass, as as has been used before.
So when we won the contract in 2002, so I wasn't here when the decision was made, so why beryllium versus ULE glass? It was actually a fight-off between Harris and their beryllium design and Kodak then with their ULE glass design. I believe what won out was at the cryogenic temperatures, the properties of beryllium and the stability within that environment just ended up being superior. There was probably some trade and debate around which one was more manufacturable, right, in terms of what you can get to. It did take us a long time to make the mirrors. Again, I wasn't a part of the decision cycle. I just know beryllium performs perfect for us at the cryogenic temperatures.
Okay. Is there any kind of a backup plan that would send a man out to space for repair?
There isn't a backup plan, but I do get a chance to talk to John Grunsfeld, the Hubble hugger, 5-time shuttle astronaut, 3-time fix-it guy. I think he said he'd volunteer if they would send him out there. But right now we have no capacity to put man out there outside of low Earth orbit. So there certainly isn't a plan to go out there and do an astronaut-supported mission.
Okay, so this is the last question. We started with questions like this, but what are some of the things that are hoped to be discovered with this telescope?
So my wishes and hopes, right, I could say within my generation that we have, definitively determined a planet out in another solar system that is supportive of life as we know it. Absolutely, hands down. That's one as a personal, curiosity. The other thing is, I'm an electrical engineer, but my wife laughs at me. I was on the Khan Academy this weekend looking at valence electrons in the periodic table. I'm a periodic table nerd. I don't know what it is. And thinking that we started off with helium and hydrogen, and now we have a periodic table and how those higher order elements, the Webb Telescope will actually go back and see literally how, that's every element that's in our bodies and our planet. So we're going to see a state of evolution of a periodic table, right? Not just a species or planet. So to me personally, I'm kind of a nerd when it comes to chemistry is my little side passion outside of being an electrical engineer. So I think of those two things as the cooler things we'll do.
All right, that wraps up our Q&A. Again, will you please join me in thanking Scott for his great presentation?